The amines represent another organic functional group, and they contain, as we see here in this first molecule, an NH2 group represents an amine. So this is an example in the top left here of what we would call a primary amine, and that would be an example of methyl amine. If we've got two carbons in the chain, that would be ethyl amine. And both of those would represent primary amines, because the amine group, nitrogen on, is only connected to a carbon. It's just connected to one other carbon. Whereas if we look at this molecule here, we've got dimethylamine. And if we look at this molecule, the nitrogen here is connected to two other carbon atoms. So that would represent a secondary amine. The nitrogen is connected to two other carbons, whereas in these primary amines, the nitrogen is connected to one other carbon. We could also have a tertiary amine. This would be trimethyl amine, in which the nitrogen is connected to three other carbon atoms. So there we've got a tertiary amine. So primary, secondary, tertiary amines are all possible. In terms of the physical properties, these amine molecules, well, they are able to form hydrogen bonds. This NH bond here that we've got is polar. So what happens here, the nitrogen, being more electronegative, we say, than the hydrogen, pulls the bonding pair of electrons that are involved in the nitrogen-hydrogen bond closer to the nitrogen, and that gains a partial negative charge. The hydrogen is partially positive, so this is a polar bond here. Let me show that again here on this molecule. And nitrogen is in group 5 of the periodic table. It has 5 outer electrons. It uses one of those electrons in this covalent bond, one in that one and one in that one, meaning it's got 2 non-bonding electrons, what we call a lone pair of electrons. And it can use that to form hydrogen bonds. So between amine molecules, you will be able to form hydrogen bonds, which we know is the strongest of the 3 intermolecular forces. So when you compare van der Waals forces, dipole-dipole forces and hydrogen bonding is the strongest one. So we're going to see here a higher boiling points than we would see certainly in alkane or alkene molecules of a similar size, and also a higher boiling point than we would see in halogeno alkanes that would rely on dipole-dipole forces. The NH bond, although it's polar, it's a little bit less polar than the OH bonds that we would find, for example, in alcohols and carboxylic acids. So the boiling point of these amines is less than we would find for a similar size alcohol molecule. So whereas the shorter chain alcohols tend to be liquids at room temperature, these will be gases. So for example, methylamine has got a boiling point of about -6 degrees Celsius. So basically it will boil at -6. It'll be a gas then by the time we get to room temperature at about 20 degrees Celsius. Even ethylamine, as the carbon chain gets longer, the boiling point will go up, but ethylamine has got a boiling point of about 16.6 degrees Celsius. So even that probably is going to boil before we get to room temperature. So these shorter chain amines will be gases at room temperature. Boiling point higher certainly than alkanes and alkenes of equivalent size, but less than alcohols. Because it can form hydrogen bonds, the shorter chain amines are going to be miscible with water. They will dissolve, they'll be soluble in water because they can form these hydrogen bonds. So for example, a water molecule here, what we know is that water forms hydrogen bonds with other water molecules, but it can also form a hydrogen bond with one of these amine molecules. That dotted line there represents a hydrogen bond interaction between the water molecule here and the amine molecule here, which will mean that this will dissolve in water. It will get in amongst the water molecules. It will interrupt the hydrogen bonding between the different water molecules to form its own hydrogen bonds with a water molecule. And hence the shorter chain amines, as I say, are miscible with water, They've got a good solubility. Solubility, just like with other organic molecules that dissolve in water, solubility will decrease as the carbon chain gets longer. So long chain amine molecules with long hydrocarbon chains will still tend to be insoluble and will not mix with water very well. The first reaction of amines that we're going to talk about is its action as a base. So here we have methylamine, this molecule on the left, and we can see on the nitrogen there is a lone pair of electrons. And this is what allows amines to act as a base. Basically, a base is something that will accept a hydrogen ion. So in solution here, these amines are weakly alkaline, weak bases, because they'll accept a hydrogen ion and they'll produce hydroxide ions. So if we've got methylamine in solution, the pH of that solution will be above 7. It will be slightly alkaline because we're producing a higher concentration of hydroxide ions here as the amine group takes a hydrogen ion and forms this ion here, this positive charged ion, and we get a hydroxide. What it also means is that amines will react with acids. So, for example, if we had, let's say, ethylamine, which would be a 2-carbon chain, and we've got the 2 hydrogens there on the nitrogen. We've got this lone pair of electrons that would react with an acid. So let's take a simple inorganic acid, hydrochloric acid. And again, because it's acting as a base, what that is going to do is going to take the hydrogen ion from the acid, form a positive ion here. So what we're going to do is we accept the hydrogen ion from the acid. The amine uses its lone pair of electrons to do that. What we're going to do is going to form a positive ion here. And a negative chloride. So we'll form this species here, which we could call ethyl ammonium chloride. Point here, the reaction that's taking place is the reaction of an amine acting as a base, reacting with the acid, accepting the hydrogen ion, which is what a base does, and forming this species here. We could call ethyl ammonium chloride. Because an amine contains a lone pair of electrons here on the nitrogen, it can also act as a nucleophile in chemical reactions. For example, with a halogenoalkane molecule, we see here we've got bromoethane. Now, bromoethane has a polar bond here, carbon partially positive, the bromine partially negative, and so the lone pair of electrons on the nitrogen enables it to form an attraction here to this partially positive carbon, and this pair of electrons forms a covalent bond to the carbon. At the same time, the carbon-bromine bond will break, and we will form basically a secondary amine. And we will form this molecule overall, we'll get that, and we will get HBr. So there we have an example of a chemical reaction involving an amine in which it acts as a nucleophile. This product molecule actually can also act as a nucleophile because the nitrogen has still got a lone pair of electrons, and so it would then not stop there, it would react with the bromoalkane again, and if we reacted that with again, and there we go, that would be the product. So I'll just shorthand there to write out the C2H5 part of the molecule. But you can see here, basically here we started with our amine there, and then 2 sets of nucleophilic substitution reaction each time. Basically we're replacing one of these hydrogens here with C2H5, and so eventually after 2 steps we would actually produce this molecule, our tertiary amine, CH3 group is still on there, but then we've got the two C2H5 and a C2H5 there. And that is an example of nucleophilic substitution with the amine molecules.